Morning. How is everybody? I see David over there sitting in the back now. Where's Stephen? Is Stephen here? Stephen Scheidler? Okay. I might have an extra one over there with you today, David. He said he might come over there instead of here. Okay, so just so you know, don't be surprised. I'm trying to get this computer going over here. It wasn't turned on, so we're letting it warm up and everything. But I'm going to show you a few things on here that what we're getting ready to look at. And I posted a homework assignment for you, so that's a little different. So we're going to look at that too, okay? Is everybody doing okay this morning? Yeah. All right, good, good.
Cold.
Cold? You cold this morning? Yeah. It's warm in this room, though. How about in your room over there? It's okay?
They keep it cold here. The janitor says it keeps out the bees, but I've never seen a bee, so I guess it works. But they love to keep this room cold for some odd reason.
Okay. Wow. So you got to wear warm clothes always then. It's pretty warm over in this room, isn't it? Maybe it's because I just walked over here from my building. I don't know. So, or because I'm always running late, so then I have to hurry. Okay, so maybe that's it. Well, I'm almost here. It's getting there. It's still swirling around on us, but it's getting there. Okay. On the screen. I'm going to switch it over. I'm going to show you first, just so I don't forget to think about this, where I posted a homework assignment. Some of you may have already seen. Did I send you an email about that? I'm thinking no, I didn't send you guys an email, did I? I can't remember if I did or didn't. I sent somebody an email. Maybe it wasn't you all, though. So I will send one. So even though I tell you in class, I'll send one later today, just to make sure everybody's aware of that. Let me go over here to D2L. That's where it's going to be posted. This is an actual homework assignment. I want you to print it off. It's only 5 questions. It's nothing major, okay? It's just to make sure you're thinking about something in this section 7.1 and 7.2, even though we are getting ready to have break. Now, the good thing is, you know, you've got this posted. It's there today. You've got tomorrow. I'm not trying to suck up your break fun, right? So you've still got Wednesday of next week because yours isn't due till Thursday. When you come to class Thursday, it's something I want you to actually print off and work, you know, write on, bring back to me to turn in, okay? It'll count like the unit circle quiz did, okay? So just another grade like that, 10 points. It goes in with that homework, My Math Lab, all that stuff works together, okay? Also over break, it'd be a good time to get caught up on My Math Lab. If you're not there yet, that'd be a great time to work on that as well. Just giving you some ideas in case you have forgotten about some of these things. I think I got that in. Let's see. So just giving you a little bit of an idea of where we might want to go with this. And the homework, it's easy to find, but I just want to show you up here and make sure that everybody can see and is aware of where it's located. So when I go down to our class right there and go to content, you're not going to see all this stuff. That's some of my old stuff. You're just going to see one thing, 1720 homework Tuesday, Thursday, okay? That's going to be your homework, and you can download it. It's probably easier to do. And I do want you to print this one off, though, and work it out and submit it as a paper, okay? It's just one sheet. Well, there it is. There it's coming. It's questions from 7.1 and 7.2. Some of them will require work, so if they do, please do work. A couple of them are calculator questions. I want to make sure you can do the stuff with your calculator, so it's nothing really major there, but 2 of them are calculators. 3 of them you got to show work, okay? Just to keep you thinking about it a little bit in the next few days. Anybody have a question about what we're doing there? Any questions about that? Nope, we're good. Okay. So we've got fall break coming up Monday and Tuesday. So I won't see you all again until next Thursday. I know that makes everybody really sad, but we'll get through it, right? We'll be back. Okay, so let's look over. We had talked in last class on section 7.3, trigonometric equations. We were solving those. We were kind of looking at the difference. This is part of why I'm giving you the homework. I want you to make sure you're seeing the difference in solving an equation or in working just with the basic inverse functions. Remember, if the question just says something like inverse sine of 1/2, this is where you have to look between negative pi halves and positive pi halves, right? And say which angle in within those boundaries has a sine value of 1/2. And so which one is that anyway? Pi over 6, right? Pi over 6 has a sine of 1/2, a cosine of square root of 3/2. If we're in an equation, it says solve this equation, and we want to solve something here. I don't know what we might want to solve. Let's see. Let's say we want to solve 2 sine theta plus 3 equals 2. And to do that, remember, we're subtracting 3. We're employing our equation solving techniques here. So we have 2 sine theta equals -1. Divide by 2, and we get the sine of theta is -1/2. And technically what we're doing is we are taking the inverse sine. I mean, we're looking at that. We're thinking, okay, I'm going to say the inverse sine of that to get rid of the sine, inverse sine of this. But because I'm putting it in there and because I'm looking for all solutions between 0 and 2 pi, I'm not restricted to negative pi halves to positive pi halves. So I'm going to get here theta equals the inverse sine of -1/2. I'm thinking of all the angles now from 0 to 2 pi that have a sine value of -1/2 in this case. I was trying to make it come out to be 1/2 like the one up top, but it didn't work out for me. Okay, so where is the sine -1/2? We would have an angle in the third quadrant and the fourth quadrant where that sine's negative. 11 pi 6 in the fourth quadrant. And what else? And 7 pi 6. They're in the third quadrant where the sine is that negative value. Okay? But we're looking for all the angles here because we are solving an equation. We want all possible solutions. We are thinking of it like an inverse sine problem overall because we're thinking backwards. We're trying to get an angle. We're thinking what angle would have this value as its sine. So we're kind of thinking along those lines, okay? But we are not limited now to the parameters because the question was not given to us as an inverse sine. Okay, it's all in how, what was the actual question starting out. Any questions about that? This was what we were doing in 7.2, and this was what we were doing in 7.3. But it's two different procedures. First one, we're just given an exact value for whatever that would be equivalent to, and the second one, we're finding all possible solutions for. All right, well, let's look at a few of these equations while we're here. There were a few types we did not get to talk about last time. You all may have encountered those. Yes, some. So maybe you want to ask one first, and let's see if that's one that we didn't encounter yet. Somebody have one you want to ask on page 460 is where I'm at.
We do 19.
Yeah, 19 is one like I'm referring to. So right there, you found it. I think 17 was one also. But 19 says the cosine of 2 theta is equal to -1/2. So this time the cosine is equal to -1/2. We just did a problem with the sine equal to -1/2. So what we want to think about here is where does the cosine equal negative 1/2. Where does that happen?
Pi thirds.
Okay, is the cosine negative 1/2 though at pi thirds? But the cosine would be positive at pi thirds, right?
2 pi over 3.
So 2 pi over 3. Where else?
4 pi.
4 pi over 3, right. Let me draw a picture here to help us see this a little bit better. There's 2 pi thirds. All the way around there, it's 4 pi thirds. That's starting at 0, pi halves, pi, 3 halves pi, and 2 pi. Now, the question here that I want to ask you also, though, if we did the cosine, let's say I go around that unit circle again, or I go another revolution around. If I go another revolution around, I'm adding 2 pi to my angles I already have, right? So let's say I add 2 pi to 2/3 pi. That gives me the equivalent of 2 2/3 pi, also known as what? 8/3 pi, right? Okay, so if I go around again, let's see, where's this one? Right there, right? Then we're at 8 pi thirds. Would it be true that the cosine of 8 pi thirds is also negative 1/2? You agree with me, right? You agree? Okay, I'm showing you this because there are other angles outside that range from 0 to 2 pi that have these trig function values. Normally, though, we're just looking for that particular value theta that will give us, just that's the value that's the angle we're finding the trig function of. So we limit ourselves from 0 to 2 pi when we're trying to answer the question. Still, theta has to be from 0 to 2 pi. But this time, the difference is I have a number being multiplied by theta. Whatever theta is, I'm going to multiply it by 2. Theta can be all kinds of things from 0 to 2 pi, but when I multiply by 2, I still may get one of these other angles that I've gotten from going around again, where it still has a cosine of negative 1/2. Now, that's not saying I'm not choosing my solutions for theta between 0 and 2 pi, but I'm using larger angles, when I do the cosine to get negative 1/2. So here's a couple of things I want you to think about here. When it says cosine 2 theta equals negative 1/2, we know that the cosine of 2 pi thirds equals negative 1/2. True? You all told me that up here. Those are not our answers, by the way. We know the cosine of 4 pi thirds is negative 1/2. We know the cosine of 8 pi thirds is negative 1/2. We could keep going. We could get what we get when we add 2 pi to the 4 pi thirds. That would be 10 pi thirds. We could also say the cosine of 10 pi thirds is negative 1/2. We're thinking about this, okay? We're not answering yet. This is some stuff we're thinking about for a minute to try to help us see where this answer is going to be. So if this stuff is true, and I'm telling you it is true, right? Then 2 theta could be equal to any of these things. If I can work that out to where 2 theta equals any of those angles that I've said have that particular cosine and get a value for theta that's still between 0 and 2 pi, then I'm getting answers, right? I'm getting solutions to my equation. So the way I would look at that, what we're actually thinking here is that the cosine of 2 theta, that the 2 theta part has to be either 2 pi thirds or 4 pi thirds. We know it could be those, plus some multiple of pi. Now, I don't always write it like this because people say, what in the heck does that mean? But what I've got here is plus 2k pi. K is just a constant. So I'm using k for a constant where I'm saying 2 times 1, 2 times 2, whatever. If I add various rotations, they're revolutions of 2 pi. Now, the way I'm going to suggest you look at this, though, is just say 2 theta could equal 2 pi thirds, right? And solve that and see what would theta have to be. We had to kind of go backwards here. We had to figure out what angle would have that cosine, and now we're having to set the argument they gave us equal to that, since our argument is not just theta this time. 2 theta, though, could equal 2 pi thirds, and when I divide by 2 here, I get theta equals, what do we get, pi thirds? 2 pi sixths, which is pi thirds. Y'all with me on that? That's 2 pi sixths, which is pi thirds. Okay, so pi thirds could be an answer because looking back at my original equation up there at the top, I have 2 times, I'm saying pi thirds for theta. 2 times pi thirds gives me 2 pi thirds. I take the cosine of that, and I get negative 1/2. You see how it's working back in that original equation? If theta is pi thirds, I get an angle that has the given cosine. Okay. What if, from this part here, what if 2 theta is equal to 4 pi thirds? Then theta is going to be 4 pi thirds divided by 2, which is 4 pi sixths, which is 2 pi thirds. So actually 2 pi thirds does appear to be one of our answers. So far we've got theta can be pi thirds, theta can be 2 pi thirds. I'm going to take these enclosure off of this up here. Well, the best I can. Okay. All right, so we've got 2 answers that are both between 0 and 2 pi. But what if I go on with those revolutions? Are there values from 0 to 2 pi that I can multiply 2 by and still get an angle that has a cosine of negative 1/2? Okay, so we're thinking a little further out now. I have 2 theta equals 8 pi thirds. So, whoops, not 2, but theta then will equal 8 pi thirds divided by 2, which is 8 pi sixths, which is 3 pi halves, right? If I multiply that 2 up in my original equation by, what do I have here? I didn't do that right. What am I doing there? Whew. Yeah, I wish you would have. Does that look better? Yeah. Whew, long morning, huh? All right. Whoa. 4 pi thirds is what we're getting there. Now, I thought when I looked back up, I thought, what? That's not looking right. 2 times 4 pi thirds. So what's that? 2 times 4 pi thirds is actually just 8 pi thirds because we're multiplying 2 over 1. 2 over 1. So, see, it's been a long morning for lots of us, right? But 2 times 4 pi thirds is 8 pi thirds. And we've already noticed up here that we have 8 pi thirds up there. You know, that's what we get when we add 2 pi to 2 pi thirds. And so we know the cosine there is also equal to negative 1/2. Our question would be then, this value for theta we got, this 4 pi thirds, is it still between 0 and 2 pi? It is. So it's still a solution to our equation because it's still located between 0 and 2 pi. When we insert it into the equation, multiply that 2 by it, we still get an angle that has the given cosine. What about this 10 pi thirds? Even though the things we're looking at, the 8 pi thirds, the 10 pi thirds, those are past 2 pi thirds. We would not give those for answers for theta. Those are not going to be our thetas. Those are the angles that have a cosine of negative 1/2. To get them, we have to multiply by 2 up there. Okay, so let's look here then. 2 theta could equal 10 pi thirds here. So theta is equal to 10 pi sixths, which is 5 pi thirds. Right? 5 pi thirds. So is 5 pi thirds still between 0 and 2 pi?
Yep.
Yeah. Now, so do I need to go around another revolution, do you think? Do I need to add another 2 pi and see what the next one would be? Or
No,
why do you think I don't need to now?
because you're 1 pi third away from being at 2 pi.
Yeah, I'm just 1/3 pi away from being at 2 pi when 5 pi thirds is 1 2/3 pi. So anything else I get out of there is sure to be larger than 2 pi because look at our little pattern here. We've got going pi thirds, 2 pi thirds, then we skipped 4 pi thirds and 5 pi thirds. So anything else we're going to get is going to be too large, right? It's going to be out of that range. Normally on these you just will need to go twice, you know, that second revolution around, normally. But that's what we're looking at here. We're looking at what makes this thing up here be an angle that has a cosine of what's given to us. So we want to set it equal to the angles that we observed just from the beginning and see what theta would equal, as well as the angles that would be, 2 pi away from that. Okay, 2 pi away from the ones that make that happen. Yeah, these are, I guess, a little tricky here. Other questions on this one?
So we need to give every single possible answer?
Yeah, because we have to give all the answers that are between 0 and 2 pi, and all of these were solutions that were between 0 and 2 pi. So in our equations, we always want to get every possible solution that would work in the equation. That's correct. Yes?
Why is 5 pi thirds an answer? Because that cosine isn't negative 1/2.
The cosine of 5 pi thirds is not negative 1/2, right? But 5 pi thirds is theta, and it goes right there. Go back up to the top of the screen with me. 5 pi thirds goes here times 2, which gives me the cosine of 10 pi thirds. And the cosine of 10 pi thirds, what's the cosine of 10 pi thirds? That is negative 1/2, right? 10 pi thirds is 3 1/3 pi. So it's ending up, you can't hardly see it now, but it's ending up back where that 4/3 pi angle is, okay, as far as the terminal side goes. So it's not these values that we're putting in and getting their cosine equal to negative 1/2, not the ones I've circled in. Those are our answers. Those are our answers for the values that we will replace theta with, but then they have to get multiplied by 2, and that's where the cosine's equal to negative 1/2. It's kind of multi-step here on that part. And I just noticed that was up there, so let's take that out too. That is where it was, but we don't need it circled. All right, what else on this one? Those are good questions you are coming up with there. Let's try another problem here. What's another equation you want us to look at today?
Number 17.
17, it's unanimous. All right. Sine 3 theta is equal to negative 1. So our question is then, where is the sine equal to negative 1? Sine of, well, we don't want to say theta, but I'm just going to ask it like this. Where does the sine equal negative 1?
3 pi halves.
3 pi halves, right? Sine's equal to negative 1 at 3 pi halves. So I'm drawing up here again. 3 pi halves is there. What if I go around again? What if I add 2 pi to 3 pi halves? Where else then would the sine equal negative 1? Where would that be? 3 pi is right up there, right? So this is going to be 3.5 pi. 7 pi halves, right?
Yeah.
Okay, so we could go around to there. Just for the heck of it, to add and make sure we're getting here. That was from the red up there. Let's go in blue. I went around again. So I'm going to add another 2 pi. Where would I be down here?
That'd be 11 pi halves.
It'd be 11 pi halves, right? Okay, each time if I'm adding 2 pi, and I'm looking at this, 3 halves pi, 7 halves pi, I'm adding 2 pi, which is the same as 4 over 2, right? So 2 is 4 over 2, and then put the pi with it. So we're adding 4 halves pi each time. So 3 halves pi plus 4 halves pi is 7 halves pi, plus another 4 halves pi, which is another 2 pi, gives us 11 halves pi. I don't know how many of these we need to use, but let's look here. 3 theta could be equal to just the 3 pi halves. And then we'd have the sign of that value is negative 1. So I'm going to get theta equals 3 halves pi divided by 3, which is 3 pi over 6. And that gives me pi halves. So pi halves should be one of my answers, okay? It is not that the sign of pi halves is negative 1, but the sign of 3 times pi halves is negative 1. Right? The sign of 3 times pi halves is negative 1. We in agreement? Well, set 3 theta equal to 7 halves pi. Let's see what we get there. Three theta could equal 7 halves pi. So what are you getting? 7 pi over 6, right? That's an answer. Because 3 times 7 pi over 6 gives us the 7 halves pi, where we've already established that 7 halves pi, the sign is negative 1. Maybe we'd better try that other one, because 7 pi 6 is just 1 1/6 pi, right?
Yeah.
So let's try that next one. We're dividing by 3. So we get 11 pi 6. Is that still good? Is that still between 0 and 2 pi?
Yep.
Yeah, barely, but yeah, right? Since it's barely, then I would say I'm done. I'm pretty close to 2 pi there with that answer. 11 pi 6, all I need to go is 12 pi 6, and I'm at 2 pi. I get these 3 answers for this one. That's how those are working. Go back and retry some of those, before next week. And the ones that have, now remember the difference with these that we're looking at now, they have a coefficient of theta in there with the angle. They have that coefficient involved, okay? So you want to go back and try some more of those. We've seen 2 examples now. So go back and retry and see if they make better sense now. Go ahead.
So that coefficient, that determines how many times you're going around the circle.
Well, it is appearing that way, isn't it? Let's see here. Can't get back there. This one we went 2 times around. We also were dealing with 2 separate places here on this one. This one we're only dealing with the one place. That could make a difference as well. So be careful. I don't want to generalize that just yet, okay? Be careful on that. I'd have to be a little more convinced.
But we're only going to 2 pi each time.
Right. Okay. Whatever the values we get for theta, we don't want them to be over 2 pi. Right? They cannot be over 2 pi. Now the values we're saying that the 3 theta is equal to, or whatever the argument is equal to, those can be over 2 pi. Just whatever we get for theta to equal, that's what cannot be over 2 pi. Okay? All right, let's see. You all were working with 11 to 29, is that right? Mm-hmm. Starting out up there in that part. And you had some on the other page too, 57. Did you have those, 57 to 79? Yeah, okay. That's what I was thinking. I was trying to find one more here that's similar, but I don't know. Let's look at 18. It's a little different. It's right there in between them, but similar yet different, but we'll give you one more thing to go by. Tangent theta over 2 equals the square root of 3. Remember your tangent's equal to y over x. So where's the tangent equal to the square root of 3 anyway? You think? Where? Pi thirds, yeah. Pi thirds, the tangent is square root of 3 because our coordinates are 1/2 square root of 3 over 2 at pi thirds. And so where else will the tangent be equal to the square root of 3? In one other quadrant.
Be 2 pi thirds.
2 pi thirds, the tangent will be negative. Because we have a negative x and a positive y.
Okay, then 7 pi, or I'm sorry, 4 pi thirds then.
4 pi thirds, okay. So we're down here at 4 pi thirds. And we're up here at pi thirds. Okay. That's where we're looking at. Is everybody with me so far? Everybody okay so far there? All right. Now we have, since the tangent is equal to the square root of 3 at pi thirds and at 4 pi thirds, those are the values that we want to start out setting our theta over 2 equal to. We're trying to see, well, how do we make theta over 2 turn into pi thirds or turn into 4 pi thirds? So we're going to be solving that equation as well as this equation. And probably more because we have that multiple there, so we'll see. Just to make sure we're getting this here, if we go around, if we add 2 pi to pi thirds, where are we there then? What would we call that?
Be 7 pi thirds.
7 pi thirds, right? And if we add 2 pi to 4 thirds pi.
You got 10 pi thirds.
10 pi thirds, right? So the easiest way I'm seeing for you to do that, to add those values, I know a lot of people hate fractions. That's probably true in here, right?
So do we have to find all possible solutions?
Yeah, we got to find all possible solutions when we're working equations. We have to. The easiest way I'm seeing for you to work with this part here is when we're adding 2 pi, and you already know the angles where you get the tangent equal to the square root of 3. The thing I'm seeing that you can do here is say 2 pi plus 4 thirds pi gives you what I would think of as 2 and 4 thirds pi. We never really answer with 2 and 4 thirds pi because that's a mixed number in with an improper fraction. So we never see those written like that. But for our purposes, they're not going to hurt anything if we have 2 and 4 thirds pi. Take 3 times 2 is 6 plus the 4. That's where we're getting that 10 up there. Just your general changing from a mixed number to an improper fraction. Or you can think of it like this. 4 thirds pi is 1 and 1/3 pi plus the 2 pi will give you 3 and 1/3 pi, right? 3 and 1/3 though is 10 thirds pi. We normally write these as improper fractions when we write these values, but you may need to think of them as mixed numbers before you go to the improper fraction, okay? You might need to. Does that help a little bit with the fraction part? Trying to give you a little tip on making those fractions a little bit easier, okay? They don't have to be tough. I promise. They don't have to be that bad. All right, so let's solve some of these things down here, okay? Starting down below this black line here, I have theta over 2 equals pi thirds. What am I going to do to solve that, to get theta?
You multiply both sides by 2.
Right, in this case, I'm going to multiply both sides by 2, and I get theta equals 2 pi thirds. Okay, theta is equal to 2 pi thirds there. So that's one value we could have for theta, and it is between 0 and 2 pi, so that's a solution. We've got to find all possible solutions from 0 to 2 pi. Okay, this next one I multiply by 2. I'm getting theta equals 8 pi thirds now. Theta is 8 pi thirds. 8 pi thirds is how much? What is it?
More than 2.
It's more than 2. So we can't circle that one. I'll have to rewrite it now. We can't use that one. That one didn't happen, okay? We don't want that one. So it looks like we're already too big. We didn't need these things where we added 2 pi. We just used those for fraction thoughts, right, today? So we didn't need those. This one's already too big for theta. So we don't use it as an answer. The only value we can get between 0 and 2 pi is where theta is equal to 2 pi thirds. So this is supporting what you said about only go so far. This time it's like we only went half, right? We only went to half of them. So halfway, I guess. We only used that first one. We didn't even go around at all. We talked about what the angles would be if we did go around, but we didn't have to use those this time because that was too big for theta. Theta has to be between 0 and 2 pi. Well, let's try another equation here, okay? We had some other types as well. We had some with quadratic type trig equations. We had some with the square root property. What else did we have? I don't know. What else did you have a question about here? Yeah.
Can you do number 61?
Okay. So we've got 13 here, 61 also there. So let me get 13 just because it's still early on, and then we'll go over to 61, okay? So 13, we have 4 cosine squared theta equals 1. This one, we have something squared on one side, but also I can get rid of that 4, so let's do that. Let's divide by 4. We'll get cosine squared theta equals 1/4. What we're going to do then is we're going to take the square root of both sides. When we take the square root of both sides, we're really thinking about the absolute value of this left side, but we normally just think of it as, okay, I'm going to do the square root of both sides from what I had here. But since I'm thinking, what can come out of that, I need to put in that plus or minus to get all possible solutions here. So I've got the cosine of theta is plus or minus the square root of 1 over the square root of 4. So the cosine of theta is positive or negative 1/2. So I want all the angles from 0 to 2 pi where the cosine's equal to positive or negative 1/2. What angles are those? Pi thirds. What else?
2 pi thirds.
2 pi thirds. And
5 pi thirds.
4 pi thirds. What else? 5 pi thirds. Okay. So that's what we get there. That one we didn't have to think about, other values and such because, we're getting other values. We're getting from all 4 quadrants, but it's just theta. It's already just theta. We're not multiplying theta by anything. Go ahead.
So when we square root it, we want the plus or minus?
When you square root, you go with the plus or minus. Here's what's really happening there. If you've got, x squared equals 1, then what you're really doing when you take the square root of both sides is you're saying the square root of x squared, we don't really know if that x was positive or negative, whatever, but we're going to talk about the absolute value of x. We don't normally put this in, but the absolute value of x has to equal 1 because we don't know what x is, right? But if the absolute value of x has to equal 1, then x has to be either positive or negative 1, and then the absolute value of it is equal to 1. We normally don't put that step right there in. We just say when we take the square root, we're going to come down, and on the numerical side, we're going to put plus or minus. And that gets all our solutions in there, okay? It gets all our possibilities. That's when you square root both sides like that. Okay. So that's 13 there. Anything else on 13? We want to go over to 61. All right, so ready for 61? Make sure we're okay to move the screen. Think so. All right, 61. We have the tangent of theta minus 1 times the secant of theta minus 1 equals 0. Okay. Tangent theta minus 1 times secant theta minus 1 equals 0. We look at this and we might be thinking about wanting to multiply those out, but we really don't need to do that. We've got 2 factors equal to 0. So that goes along with that 0 factor property to where if I'm multiplying 2 things and I get 0, at least one of them, could be 0. So what we want to do here is just take each of our factors and set them equal to 0. So we just want to split them off like that, okay, like it's come from a quadratic type equation, even though it wasn't. But What we want to do here, we've got this factorization already set up for us. So if you've got a factor times a factor equals 0, just put them both equal to 0. When we do that, we get tangent theta equals 1. So what is theta? Where is the tangent equal to 1?
Pi fourths.
Pi fourths and
5 pi fourths.
5 pi fourths is too big. What did you say back here?
I said 5 pi fourths.
Oh, I'm sorry. Yeah, 5 pi fourths. What am I thinking today? Gosh. For some reason, you know what I was thinking? I was thinking like 9 pi fourths when you said 5. Okay, 5 pi fourths, right. Third quadrant, okay? So we're in quadrant 1 there, and we know the tangent's also positive in quadrant 3. My bad, sorry about that. Okay, so 5 pi fourths there. And then over here, the secant is equal to 1. And when I see secant, I like to think about cosine. So the cosine, though, is equal to the reciprocal, which is also 1. So where's the cosine equal to 1? Okay, so theta is equal to 0. And you said 2 pi, but what did these things say we had to be between? Yeah, we're just going to use 0. That's a little tricky because they give us those parameters and they don't want us to include 2 pi, even though that's true. But so the cosine of 0 is equal to 1. So we just get the 3 solutions here, 0, pi fourths, and 5 pi fourths. Okay? 0, pi fourths, and 5 pi fourths. Does that help clear up 61 there? On that one? Okay, we're good there. What's another one? I know we're doing a lot of these, but I just want to make sure we get them. There's so many different types in here. Yes? What about 29? Okay, let's go down to 29. And 29 was the last one I asked you to do in that first part, I think. 29, we're going to subtract 2. Starting out, 3 square roots of 2 cosine of theta equals negative 3. Then we're going to divide by 3 square roots of 2. So that we get cosine of theta equals negative 1 over the square root of 2. We want to know where the cosine is negative 1 over the square root of 2. You might want to rationalize that negative 1 over square root of 2. Because I think it'll look more familiar when you see it's negative square root of 2 over 2. So where's the cosine? Where is our cosine equal to negative square root of 2 over 2?
That'd be at 3 pi fourths and 5 pi fourths.
3 pi fourths and 5 pi fourths, right. Okay. I think on that one, was it just where it wasn't rationalized when you got it? So when you've got that radical in the denominator, if you don't recognize it, you might want to go ahead and rationalize that. There's another problem here somewhere I wanted us to look at. I don't think anybody's said further in the 60s yet, but there's one here. Where was it? 65. Let's look at 65, okay? We good on this 29? All right, 65. Sine squared theta equals 6 times the cosine of negative theta plus 1. I see a couple of things in here that might cause you to, have a question maybe. What do you see? Maybe there's nothing. Maybe I'm wrong, but this one just looked a little bit like it might be questionable. What do you see?
We got theta on both sides.
What's up? You got theta on both sides. Okay. What else? 2 different trig functions. Anything else? One of the thetas is negative. That might bother us. Maybe. Right? It might. Okay. So let's see what we can do with this. First off, I see we've got 2 different trig functions. We know how to take care of that. Use of one of our identities. So over here on the side, I want us to recall sine squared theta plus cosine squared theta equals 1. Okay, if that is so, then I could easily replace the sine squared theta with what? Sine squared theta is 1 minus cosine squared theta. That's correct. Okay. So 1 minus cosine squared theta equals, and on the right side, I can go ahead and distribute that 6. So I'll say 6 cosine negative theta plus 6. Now another thing I want to recall here is my even-odd properties. Remember even-odd properties where if we had the cosine or sine or any other trig function of a negative angle, we could work with that and make the angle become positive. But how? First off, let's remember, cosine was even or odd? Was cosine even or odd? It was even. Only 2 functions were even, the cosine and the secant. That was it. Which told us that if we had the cosine of negative theta, that was the same as what? Cosine of theta. Okay. The cosine of the negative of an angle is going to be the same as the cosine of the angle itself. Remember those? Here's an example, okay? The cosine of negative pi 6. This would be saying that's the same as the cosine of pi 6. Cosine of negative pi 6 and the cosine of pi 6 are both what?
They're both square root of 3 over 2.
Right, they're both square root of 3 over 2. All right, so that's just kind of illustrating that property. The cosine of negative theta is the same as the cosine of theta, because we went out the same distance on the x-axis whether we went to the positive or the negative of the angle. We went out the same way on the x-axis there. All right, so what we want to do up here then, in our problem, we've got 1 minus cosine squared theta equals, instead of leaving that 6 cosine negative theta, let's make it 6 cosine theta then. Because the cosine of negative theta, we just said, is the same as the cosine of theta. And then plus 6 there. What else do we want to do here? What type of equation is this? How are we going to have to solve it? We're going to have to factor. So before we can factor it, we need to set it equal to 0. Now, I'm going to get 0 on the left side because I want to get that minus cosine squared theta over to the right so it'll be positive. I just think it's easier to work with that way. You could get everything on the left or everything on the right. That's up to you. But what I'm going to do is clear out this left side. I'm going to add cosine squared theta to both sides. And I'm just writing it there. It does not actually combine with that cosine theta term because cosine theta and cosine squared theta terms are not like. Just like x squared and x terms don't actually combine together. I'll have to subtract the 1 if I'm clearing off the left side. What I've done there is I've just cleared everything from the left side by doing the opposite operation.
How come we didn't add the 6 to negative theta?
How come we did not add the 6? The 6 was being multiplied by this whole term, cosine. That goes together. That cosine negative theta is all together, so it's 6 times cosine negative theta. Okay? Yeah, it's not separate there. So now we have 0 equals cosine squared theta plus 6 cosine theta plus 5. Right? Now it looks like something we can factor. Can we factor here now? 0 equals, there's no greatest common factor. I'm setting up my parentheses here. 0 equals, we have cosine theta times cosine theta to get cosine squared theta, correct? And since it was a 1 cosine squared theta, we can look at that last term, that 5, and say, what can we multiply to get 5? That we can somehow add together to get 6, the middle term.
5 and 1.
5 and 1. That works. 5 and 1. What signs do I need in my parentheses?
Positive.
Positive, because they were all positive in the trinomial. So I need them all positive here. Is everybody with me on the factoring? Anybody have a question on the factoring? All right. What do we do now? Set both equal to 0. So we've got cosine theta is equal to -5 there. So what angle has a cosine of -5? There isn't one, is there? All the cosine values we got out, when we have cosine of an angle equals something, what does it equal? Values from where to where? The angle would be, the angles are 0 to 2 pi that we look at on that unit circle, but what's the cosine values, the x coordinates that we're looking at here?
It's -pi-halves to pi-halves, isn't it?
No, those are angles you're giving me, okay?
Oh.
Those are angles. What kind of cosines do we get for the angles that we've looked at? For any of them? It's from -1 to 1, right? The values we get for the cosine, that's what we're looking at here. This is saying that our cosine is going to be -5, but our cosine values are only from -1 to 1. Unless we have something multiplied out front times the cosine, then we might get something like that, but just to say the cosine of an angle is -5, that's not going to happen. Think about your graph. Think back to the graph of y equals cosine theta. Remember that graph? How did it go? Where's it going from? -1 to 1, right? Nothing was below -1. Nothing was above 1. So in this case here, this is just, we don't have an answer for this part. I'm just going to mark it out because we don't have an answer there. Now, if I don't get an answer for this other part, then I'll have to say there's no solution for my equation because that part is not giving me a solution. I don't want to say no solution just yet, though, because the other part here might give me an answer. It might give me something that works. Cosine theta equals -1. What angle has a cosine of -1? Pi does, right? So it gave me an answer. So all I want to list as my answer here is just the answer is pi. I don't have to say anything about that other part. I just have to know if I get the cosine of theta equals something larger than 1 or smaller than -1, then that part is not generating an answer for me. It's not going to give me anything useful. Same if it said sine of theta, something larger than 1, less than -1, that part will not give me an answer. Okay, so that's something else we needed to see today. So this one started out looking like it might give us some type of problem, but then it ended up with something we did need to see there. Any questions about 65?
So you ever get like cosine is greater than 1, it's completely worthless?
Right, if you get cosine theta is 2, 5, 7, whatever, then that part is of no use to you. You're not getting any answer from that. If they both give you, if both of these factors gave us stuff like that, then we'd have to say no solution for the whole equation because we're not getting anything. But here this cosine theta plus 1 factor did give us a solution. All right, so you all have some equations still to go back and practice with, but I want to start just briefly in that next section to get you to start thinking about that as well. And so here's where we're going with it. Here's what I want you to see today. In 7.4, we're talking about trigonometric identities. You're thinking probably we just talked about some identities, didn't we? We talked about the even odd properties. We talked about sine squared theta plus cosine squared theta equals 1. In this section, what we're going to want to do is we're going to be simplifying some trig expressions. We might be multiplying them together. We might be adding them, different things like that. And then eventually, though, we're going to do what we call establish the identities, which just means we're going to basically prove or verify that one side is equal to the other. Now, in an identity, that's all that really means. Identity just means that one side's identical to the other. Two sides are identical. We've seen a lot of the basic identities, and I'm hoping they're up here, or they're going to be soon, right? Okay, so we've seen a lot of the basic identities. I'm going to relist those for you. They are in your textbook over here on page 465. The ones that I'm thinking are going to be in your head or already are. We've been working with them already. But they go like this. We have the tangent of theta equals sine over cosine. You all know that one. These are the ones we studied back in the last chapter as well. Cotangent of theta is the cosine of theta over the sine of theta. The cosecant of theta is 1 over the sine theta. So now I'm working on my reciprocal identities. Remember those. Secant theta is 1 over cosine theta. Cotangent theta is 1 over tangent theta. Sine squared theta plus cosine squared theta equals 1. That's a basic identity that we want to have in our head. And we know from that we can get things like we just used a while ago, that sine squared theta was 1 minus cosine squared theta. We could get cosine squared theta as 1 minus sine squared theta. So we can generate some others from these Pythagorean identities at least. The other ones were tangent squared theta plus 1 is equal to secant squared theta. And cotangent squared theta plus 1 equals cosecant squared theta. Okay. So those, I think we've all worked with those, hopefully to where you have all those pretty well set in your head. Maybe those last two might be a little tougher to remember. I don't know. And then we have the even-odd property. So we also want to recall those and be able to, know what to do with that. So I'm going to start with the one we just used. Cosine of negative theta is the cosine of theta. And likewise for the other even function, the secant of negative theta is equal to the secant of theta. Those are our even functions. And then for our odd ones, we have the sine of negative theta was equal to negative sine theta. The cosecant of negative theta is negative cosecant theta. The tangent of negative theta is negative tangent theta. And the cotangent of negative theta is negative cotangent theta. These identities are what's going to really help us be able to verify or establish these others in this section 7.4. It's going to be like working puzzles in this section. And that's what we're going to compare it to. You all can tell me if you agree after we finish this section next week. But what I want us to see today, though, is how to simplify a few expressions here. We're not going too far in this section just yet, but I want you to see how to simplify some expressions here. Okay. Some of you are still writing these down to remember them, and they've got them listed in a yellow box over on page 465 in your book, really laid out nice there. I'm going to use some of the problems from, starting out from example 1 on page 466 in the textbook. I won't write them up here, though. Okay, but that's where I am. Everybody got the identities that you need? Those are your tools. That's what's going to help us do this, okay? That's why we want to have these things in our head, because they're what we need. If you're going on to calculus, you'll use that whole page of stuff I just put up there. You still need to know that for calculus. Okay, so several of you have indicated you are going that route, so keep that handy somewhere. Okay, cotangent theta over cosecant theta. Let's simplify this by writing only in terms of sine and cosine. So we're just going to follow the directions. It says to simplify this by rewriting the trig functions in terms of sine and cosine functions and see what you get. So we've got this thing, cotangent theta over cosecant theta. The cotangent up there on the top, cotangent is what over what? How should we write that? Cosine over sine, right. Cosecant, 1 over sine. So we've rewritten it, but we never leave anything as I can't think what it's called, a complex fraction like this. We never leave anything with all these fractions involved in it. We need to simplify that, break it down, We know that this means the cosine of theta over the sine of theta divided by 1 over the sine of theta. But that will be the same as the cosine of theta over sine theta times sine theta over 1. Right? So what does this give me?
Cosine theta.
Yeah, just cosine theta. So you've just kind of created an identity there, or you've just kind of seen it happen. Cotangent theta over cosecant theta is equal to the cosine of theta. Who knew, right? You're saying, who cared? No. Okay, well, so we're simplifying it. We're breaking it down. We're seeing, there's other things we can do with these. We can work with them. We can make them appear differently, even though they're still equal to what we started with. It's kind of like when we have 2/5 and we multiply both parts of that maybe by 3. And so we say we've got 6/15. And 6/15 is the same as 2/5. Right? We just changed how it looks. That's what we did here. We changed the looks of cotangent theta over cosecant theta. And we see that could be cosine theta. So we're going to be doing a little bit of manipulation here to turn something into something else. Let's try another one here, okay? This one, this time I'm going to take number 12 from page 469. It tells me to multiply. Here's what I'm multiplying. Sine of theta over 1 plus cosine theta times 1 minus cosine theta over 1 minus cosine theta. Now, that's what we just did with that fraction, wasn't it? We multiplied by 3 over 3, a form of 1. Here we're multiplying by 1 minus cosine theta over 1 minus cosine theta. That's also 1. We're just going to be changing the looks of what we started with here. So typically when we start out multiplying, we're just going to write down what we're multiplying. I'm multiplying the top of the numerators there, multiplying the denominators together. Now when you're doing these, sometimes something will end up canceling out with one of your factors, especially like on top we've got that sine theta out there. I probably would not multiply that top part out just yet. I would leave it until I see what I get in the denominator and see if something might cancel out with that sine or with the 1 minus cosine theta. Also, right here at this step, I want to caution you, a lot of times people want to go in and mark out both those 1 minus cosine thetas, but that's, we don't want to do that here. We're trying to change the form from what it did look like to something else, since they specifically are telling us multiply by this. We don't want to cancel just yet there. So what we're going to do is we're going to write out sine theta times 1 minus cosine theta. I'm just going to leave that alone for a minute. What will I get, though, when I multiply out the denominator? Okay, 1 squared minus cosine squared theta, which is just 1 minus cosine squared theta, right? Okay. And you're foiling here. You've got 1 squared minus cosine theta plus cosine theta. Those, go away. They negate each other. And then minus cosine squared theta. Now, I got to be thinking here a little bit, though, about my identities. Can I change any of these to something from that identities
The
page?
1 minus cosine squared theta could be changed to sine squared theta.
The 1 minus cosine squared theta should be changed to sine squared theta, because 1 minus cosine squared of an angle is equal to sine squared of the same angle. And that allows us then to do what? Yeah, sine into sine squared, so it's going to leave me a sine theta down here. So I get 1 minus cosine theta over sine theta. So that is the same as what I started with up there. They're equal to the same thing. There's another way I can write this. Do you see where this would come from? Let me ask you if you see. Cosecant theta minus cotangent theta. It could be written like that. Put my or here. How did I get there?
Cosecant is 1 over sine.
Yeah, so you see what I'm doing, I'm separating it. 1 over sine minus cosine
Over sine.
because we could break that up like that, couldn't we?
Yep.
We can break up the fraction, put them both over that same denominator. I mean, they're already over it. So if I've got 1 over sine theta minus cosine theta over sine theta, that is the same as 1 minus cosine theta all over the common denominator sine theta. In your textbook, for one like this, they leave it right now at 1 minus cosine theta over sine theta, but I think it's important to note that we could break that apart, split it up a little bit there and say it's cosecant theta minus cotangent theta. We're not getting answers here this time like angles or coordinates. This is a little bit more, I don't know, maybe analytical. This whole chapter is called analytic trigonometry, so this is analyzing in a different way using our identities. Does anybody have a question on anything we did on this one? Some people don't like this section. You can form your own opinion as we go here. Okay, let's get a common denominator for two of the expressions here. This is back on example 1 again on page 466. We want to simplify 1 plus sine u. Oh yeah, they don't always use theta. You can make it theta on your paper, I guess, if you want to, but 1 plus sine u over sine u plus cotangent u minus cosine u over cosine u. Here's what we want to do. I should say instead of get, let's make it rewrite with a common denominator. We know if we add two fractions, we have to have a common denominator in order to combine those. So we want to rewrite here with a common denominator. What's the deal with a common denominator anyway? How do we get those things? Okay, lots of times we just multiply the denominators together because that will definitely give us a value that both the denominators will divide into. Okay, that will work. And that's what we need to do here because sine u and cosine u are different from each other. So in order to get a common denominator, I'm just going to have to multiply them together. Sine u, cosine u, and I'm going to adjust my fractions to have this for their denominator now. Okay, that's what I'm doing now. I'm going to adjust my fractions to get that denominator there. All right. Come over here for this commercial break now, just a moment. 2/7 plus 4/5. Thinking back. What's my common denominator here?
35.
35. I went from there to there already. What happens up here? I've got to multiply by 5 because that's what has happened to the denominator. And what about over here? By 7. Both those got multiplied by 7 or are going to. If you change your denominator, then you have to make sure the numerator goes through the same change. Okay, we have to make sure that that happens. So here what we're going to have then is, then we add our numerators, keep the denominator. Okay? This is exactly what we're going to do with the trig functions. It's going to look different. I'm telling you, it's going to be the same procedure. So that's what we did with just regular fractions. Now we come back here. I'm going to draw this arrow just to point and say, what did we do? What happened from the old denominator to the new one? What happened? Looks like we multiplied by cosine u, right? That's got to happen to the numerator as well. So I'm going to have cosine u times what I did have up there, 1 plus sine u. Okay. Over here, what happened? Same thing's got to happen there. What is it?
Multiplied by sine u.
Yeah, we multiplied by sine u. So sine u times what we had in the numerator. So what do we get now? We're going to go to one fraction now and put everything on top kind of together. My one denominator, sine u, cosine u. On top, I see I need to multiply some things out before I can really combine anything. So if I multiply these out, what do I get on top? What do you get when you multiply on top? We're starting here. Okay, cosine u plus cosine u sine u. Plus sine u cotangent u. Are we getting it? That's the distributive property, right? We just have a lot of sines and cosines in here now. So we're taking whatever's on the outside of the parentheses, multiplying it by all the terms on the inside of the parentheses, writing down what we get. What can we do now? Okay, so this was positive, this was negative, but those are the same thing. It doesn't matter if it says cosine u sine u or sine u cosine u, right? 2 times 3 is the same as 3 times 2. Multiplication has that commutative property going on, where it doesn't matter what order we multiply in. So we've got those parts. They're actually just adding to 0. So now it looks like we're left with cosine u plus sine u cotangent u over sine u cosine u. What else can we do there? All right, so we're going to try that. We're going to rewrite cotangent as cosine u over sine u. Oh, good. That allows us to cancel out the sines. That's right, because this first one's sine over 1. So we're multiplying there. That allows us to cancel the sines. What does that give us now? What do we have on top? 2 cosine u over sine u cosine u. So we're still not done, are we? We can do what now? Now we can cancel those cosine u's. So I've got, this is a long problem. Longer than I thought. 2 over sine u. I'm sorry, where's that? Oh, we added the cosine u plus cosine u and got 2 cosine u, right? And so then now we just canceled the cosine u's. So we've got 2 over sine u. There's actually one more way I could write that. If it's 2 over sine u, what's that the same as? 2 cosecant u, right? So you could write it that way. They might leave it 2 sine u. They might write it 2 cosecant u. In your textbook, they just left it 2 over sine u at that point. But we should be observant and see, because sometimes we might need to change it to the other one, okay? We're thinking these things out, okay? We're simplifying expressions. We're thinking of identities to plug in place of them. Like you said, put in place of cotangent u, put cosine u over sine u. We're seeing what we can do with them here, okay? We're manipulating them a little bit, making them look like different things than what we started with, but knowing they're still equal to what we started out with. Well, that's just really just barely getting into section 7.4. I'll just say that's a very short way into it. I'm going to ask you to try some of those problems, though, there at the beginning. Maybe look back over that example 1. That's a good example to look at. But in the beginning of section 7.4, for practice, starting on page 469, I would like you to try, not very many here, but let's try 9 through 17 odd. We'll see what we can do with those. Then remember, you have that homework on D2L that you need to print off and do and turn in due, when does that due again? Thursday, and that will be October the 16th. Okay? And then, of course, you've got my math lab quizzes you can be working on. Study identities. Make sure you know the unit circle, all that stuff. So if you get bored, over the weekend, over the break, you've got things to do. But have a great break. I'll see you back next week, okay? Thank you all. Yeah.
11 through 29 on, and 57 through 79 on work.
Thank you.
Thank you.
Sorry.
Oh, yeah. Yeah. That would be Oh, okay. Where were you? Okay. The very last thing. Well, we're going to work on that more next week. So don't, if that's all that's bothering you, don't worry about that. We'll work on that next week. We'll come back, okay? So you have to just check those notes too after you come back, okay? All right. Hey there.
All right, the homework online.
It's on D2L. It's under content. Okay. All right. Thank you. And did you sign the roll?